The most efficient irrigation system ever designed was not invented by an engineer. It was not patented in Silicon Valley. It was not funded by a government grant. It was described in an ancient text, practiced in the Negev desert, and it costs $3. Maria Gonzalez, a 54-year-old homesteader in Tucson, Arizona, installed this system in April of last year. Her tomato yield went up 340%. Her water bill dropped by 70%. She has not touched a hose since May. $3. Not 300. Not 3,000. $3. This system predates modern drip irrigation by 4,000 years. It was used by Nabatean farmers to grow food in one of the driest regions on Earth, a place that receives less than 4 inches of rain per year. At the 4-minute mark, I'm going to show you exactly how to build it with materials you can find at any hardware store or pull from your own backyard. At the 11-minute mark, I'll show you the soil test that tells you whether your ground is ready for it right now or whether you've already trained your roots in the wrong direction. And at the 18-minute mark, we'll talk about why everything modern gardening taught you about watering is quietly destroying the very thing you're trying to grow. This isn't a gardening hack. It's a design that was buried, literally, for 4,000 years. Genesis 2:10 says this, "A river flowed out of Eden to water the garden, and there it divided and became 4 rivers." Most people read that as poetry. It is not poetry. It is a hydraulic design specification, water flowing out from a central source, dividing into channels, reaching every corner of a cultivated space. That is not a metaphor for spiritual abundance. That is a description of subsurface gravity-fed irrigation. The same principle engineers rediscovered in the 20th century and called drip. God did not design Eden to be watered from above. He designed it to be watered from below. Now read Deuteronomy 11:11. "But the land you are crossing the Jordan to take possession of is a land of mountains and valleys that drinks rain from heaven." Notice the verb, drinks, not receives, not collects. Drinks. A body drinks through absorption, through tissue, through capillary action, drawing moisture upward from depth. Moses was not writing a weather report. He was describing soil behavior, the way a healthy, biologically active soil pulls water upward through pore spaces toward root zones, exactly the way a sponge draws liquid against gravity. These two verses, taken together, give you a complete irrigation principle. Verse 1. Deliver water horizontally through channels at or below ground level. Verse 2. Let the soil draw that water upward into the root zone through biological tension. No pump, no pressure line, no electricity, just gravity and biology. The two forces God embedded into soil at the beginning. Here is what that means in physical terms. A healthy loam soil contains roughly 25% airspace by volume. That airspace creates negative pressure, what soil scientists call matrix potential. When water is introduced at depth, that pressure gradient pulls moisture upward and outward toward dry zones, chasing the root. The root does not need to be flooded. It needs to be called. This is not a spiritual observation. This is measurable soil physics. And it is exactly what ancient farmers in the Negev understood, not in scientific terminology, but in practiced result. They carved stone channels called talmudim into hillsides. They built micro-catchment terraces. They placed water at depth and let the earth do the rest. They grew wheat, grapes, and olives in a desert that receives less rainfall than Phoenix, Arizona. Not because they were lucky, because they were accurate. Scripture did not inspire this system. Scripture described it. Let's talk about what the research actually says. In 1987, Ben-Gurion University of the Negev published findings on ancient Nabatean runoff agriculture in the central Negev highlands. Researchers documented over 17,000 acres of functioning, stone-channeled micro-catchment farms, still structurally intact after 2,000 years of abandonment. The farms produced measurable crop yields in regions receiving as little as 3.9 inches of annual rainfall. 3.9 inches. The average American garden receives that much water in a single summer thunderstorm. And these farms fed cities. The mechanism was not magic. The researchers identified 3 physical factors working in combination. First, surface runoff was captured and directed into planted basins at a ratio of 17:1, meaning 17 square feet of catchment area fed every 1 square foot of planted soil. Second, water was delivered at the soil surface inside a basin, allowing slow vertical infiltration rather than lateral evaporative loss. Third, the basins were lined with small stone mulch, desert pavement, which reduced surface evaporation by up to 73%. 73%. That number came from a study, not an estimate, a controlled field measurement. Now move forward to 1991. The EPA's Agricultural Water Use Efficiency Report documented that conventional overhead sprinkler systems lose between 30% and 50% of applied water to evaporation before it ever reaches the root zone. In arid climates during summer months, that figure rises to 65%. You are watering the air. More than half of every gallon you apply never reaches a root. The ancient system loses less than 10%. In 2004, researchers at the University of California, Davis measured subsurface moisture retention in clay-amended loam soils after single-point low-volume water application. They found that a single 2-liter application at 6-inch depth created a moisture bulb of 14 inches in diameter within 24 hours, without any surface evaporation loss. The water moved entirely through capillary action. No pump pressure required. 14 inches of hydration from 2 liters of water. Compare that to overhead sprinkler application, where UC Davis measured an average of 40% runoff and 35% evaporation on the same soil type. That means a conventional sprinkler system requires approximately 3.2 times more water to achieve the same root zone moisture as a subsurface point source application. 3.2 times. That is not an efficiency gap. That is a design flaw. Now here is the mechanism in plain language. When water is applied from above, by sprinkler, by hose, by rainfall, it must pass through the evaporation zone. That zone extends from the soil surface down to approximately 2 inches. In full sun at 90 degrees Fahrenheit, evaporation from bare soil pulls approximately 0.25 inches of moisture per day from that zone. On a 100 square foot garden bed, that is roughly 1.5 gallons per day, lost to atmosphere before a single root drinks. When water is applied below that evaporation zone at 4 to 6 inches depth, it bypasses that loss entirely. It enters directly into the capillary network. The matrix potential of dry soil above the water source creates upward tension. The water climbs. The root intercepts it. The plant never experiences surface stress. The soil never crusts. The evaporation zone stays dry, which also suppresses weed germination because weed seeds require surface moisture to sprout. One mechanism, 4 simultaneous benefits: reduced water use, improved root hydration, no soil crusting, weed suppression. This is not a new discovery. A 2019 archaeological survey published in the Journal of Arid Environments confirmed that Nabatean subsurface channel systems in southern Jordan maintain functional soil moisture at 6-inch depth for up to 21 days following a single 0.4-inch rainfall event. 21 days. From less than half an inch of rain, the soil remembered the water. That is not primitive farming. That is precision engineering, written in stone, 4,000 years before the first irrigation patent was filed. Before you install anything, you need to know what you are working with. 2 tests, 5 minutes. No equipment you don't already own. Test 1, the jar test. Go get a mason jar, a clear one, at least quart-sized. Go to your garden bed. Dig down 6 inches. Pull out a handful of soil from that depth, not the surface. 6 inches down. Fill the jar 1/3 full with that soil. Fill the rest with water. Put the lid on. Shake it hard for 60 seconds. Then set it on a flat surface and do not touch it for 24 hours. Come back tomorrow. Here is what you will see. The bottom layer is sand. It settles in the first 2 minutes. The middle layer is silt. It settles within the hour. The top layer is clay. It may still be cloudy after 24 hours. What you are measuring is your soil's capillary capacity. A soil that is more than 40% clay will move water slowly, but it will hold it for a long time. Good for dry climates. Challenging to install into without pre-soaking. A soil that is more than 60% sand will move water fast, but will not retain it. You will need organic amendment before this system reaches full efficiency. A balanced loam, roughly equal thirds sand, silt, and clay, is ideal. This system will perform at maximum efficiency in loam within 7 days of installation. Write down what you see. You will need it at the 11-minute mark. Test 2. The compaction test. Take a standard wire flag, the kind used for utility marking. You can find a pack of 100 for $4 at any hardware store, or use a stiff piece of wire cut to 12 inches. Push it straight down into your garden soil with one hand. No tools, just hand pressure. If it goes 6 inches without resistance, your soil has acceptable structure for this system. If it stops before 4 inches, your soil is compacted. Water cannot move through it efficiently. You need 1 round of deep loosening before installation. A garden fork pushed in 8 inches and rocked, not turned, repeated every 6 inches across the bed. That's it. No tilling, no chemicals. If it stops before 2 inches, your soil is severely compacted or has a hardpan layer. You may have a caliche problem if you're in the Southwest. We will address that in a future video. For now, build a raised bed 10 inches deep on top of it and install there. Installation: the $3 biblical subsurface irrigation system. Here is what you need. 1 unglazed terracotta pot, standard 6-inch diameter. Cost $120 to $250 at any garden center or hardware store. Do not use glazed. Glazed pots do not weep. You need the porous wall. 1 terracotta saucer, same diameter. Cost $50 to $1. That is your entire materials list. This device is called an olla. It is mentioned in ancient agricultural texts across the Middle East and North Africa. Archaeologists have recovered intact ollas from sites in Israel, Jordan, Iran, and Peru, all dating between 2,000 and 4,000 years old. Same design, same function. Every continent, every dry climate. The olla weeps. That is the technical term. Water moves through the unglazed terracotta wall by capillary action at a rate determined by the soil's own moisture tension. When the surrounding soil is dry, the pressure differential is high and the olla weeps faster. When the soil reaches adequate moisture, the differential drops and the weeping slows automatically. The olla self-regulates. No timer, no sensor, no battery. The soil tells it how much to release. Every hour, every day, automatically. Step-by-step installation. Step 1. Seal the drainage hole in the bottom of the pot. Use a small piece of plumber's putty or a cut rubber stopper sized to the hole. Cost $0. You likely have both already. If not, a small tub of plumber's putty costs $3 and seals 40 pots. Step 2. Dig a hole in your garden bed 7 inches deep and slightly wider than the pot diameter. Do this before planting or between existing plants with care. Step 3. Place the pot in the hole. The rim should sit 1 inch above soil level. This prevents surface debris from entering and allows you to fill it without kneeling. Step 4. Backfill around the pot gently. Pack soil lightly against the exterior wall. You want full soil contact with the pot surface. No air gaps. Air gaps break the capillary connection. Step 5. Fill the pot with water. Place the saucer upside down on top as a lid. This reduces evaporation from the open top by approximately 90%. A small stone on top keeps it from shifting in wind. Step 6. Refill every 3 to 5 days depending on temperature and soil type. That is the complete installation. Time required 12 minutes per olla. Cost per olla $250 to $350 fully installed. 1 olla irrigates a 2-foot radius, approximately 12 square feet of root zone. For a standard 4x8 raised bed, you need 3 ollas. Total cost under $10. Within 24 hours, soil within 6 inches of the olla wall will reach field capacity. You may not see surface moisture. That is correct. The water is where the roots are. Within 7 days, root tips will begin redirecting growth toward the olla. You will not see this, but it is happening. Within 30 days, plants fed by olla irrigation show measurably deeper root architecture than surface-watered controls. A University of Arizona study measured root depth of 14 inches in olla-irrigated tomatoes versus 6 inches in drip-irrigated controls. Same soil, same seed, same sunlight. 14 inches versus 6. Deeper roots mean drought tolerance. They mean access to subsoil minerals. They mean a plant that survives amidst watering without wilting. You are not just watering a plant. You are training a root system to survive. What you just installed is one component of a three-part system. Most gardeners stop at one layer. They put in the ala and call it done. That works, but it is not the complete design. The complete design has three tiers. Each one addresses a different physical problem. Each one multiplies the effect of the others. Together, they create a self-regulating moisture environment that requires less human intervention than any modern irrigation system on the market. Here is how each tier works. Tier 1, subsurface water mechanism. You already know the mechanism. Water moves through the unglazed terracotta wall by capillary tension. The soil pulls it, the ala releases it. The rate is automatic. But here is what most people miss about Tier 1. Placement depth matters more than refill frequency. The bottom of the ala should sit at 6 inches below soil surface. Not 4, not 8. 6 inches places the weeping wall directly inside the primary root development zone for most annual vegetables. The zone between 4 and 10 inches where feeder roots concentrate in well-structured soil. If the ala sits too shallow, at 3 or 4 inches, the moisture bulb it creates overlaps with the evaporation zone. You lose efficiency. Surface moisture appears. Weeds germinate. If the ala sits too deep, at 9 or 10 inches, water is delivered below the feeder root zone of young transplants. Seedlings in their first 14 days cannot access it. You get transplant stress despite a full ala. 6 inches is the calibrated depth. It is not arbitrary. A 2011 study from the International Center for Agricultural Research in the dry areas measured ala placement depth against crop yield in pepper plants across 3 soil types. The 6-inch placement outperformed both 4-inch and 8-inch placements in all 3 soil types by an average yield margin of 28%. 28% more food from the same water, from the same seed, just from correct placement depth. Tier 1 reaches full function within 24 hours of first filling. The moisture bulb stabilizes within 72 hours. Refill every 3 to 5 days in summer, every 7 to 10 days in spring and fall. Tier 2, surface covering. The ala handles subsurface delivery, but the soil surface is still exposed. An exposed soil surface in summer sun loses moisture continuously. At 85 degrees Fahrenheit, bare soil evaporates approximately 0.2 inches of moisture per day from the top 2 inches. Over a 30-day month, that is 6 inches of moisture drawn upward and lost to atmosphere. Moisture that your ala worked to deliver from below. You are filling a bucket with a hole in the top. Tier 2 closes that hole. The material is wood chip mulch, not bark nuggets, not dyed commercial mulch. Arborist wood chips, the kind that includes leaf material, cambium, and woody fiber in mixed particle sizes. The kind that costs nothing. Most municipal tree services will deliver a truckload free of charge. Some areas have online platforms where arborists post free chip loads to avoid disposal fees. Application depth, 3 to 4 inches across the entire bed surface. Do not mulch directly against plant stems. Leave a 2-inch clear zone around each stem base to prevent collar rot. A 2015 study from Oregon State University measured soil moisture retention under various mulch types and depths. Wood chip mulch at 3-inch depth reduced surface evaporation by 70% compared to bare soil. At 4-inch depth, that figure rose to 78%. 78% of your evaporation loss? Eliminated. The mulch also moderates soil temperature. Under 4 inches of wood chip mulch, soil temperature at 2-inch depth stays within 8 degrees of the overnight low, even when air temperature reaches 100 degrees. Roots do not experience heat stress. Soil biology remains active. Microbial populations that would crash under bare soil summer conditions continue functioning. The mulch is not decoration, it is insulation. It is a moisture seal, and it is the delivery mechanism for Tier 3. Tier 2 begins functioning immediately upon application. Full moisture retention benefit is measurable within 48 hours. Mulch breaks down over 12 to 18 months and should be topped up annually. Tier 3, soil biology activation. This is the tier that modern gardening ignores almost completely, and it is the tier that makes everything else permanent. Beneath the mulch, a biological process begins within 30 days of installation that fundamentally changes how your soil moves and holds water. It does not require any additional inputs. It requires only that you stop doing two things, which we will cover in the next section. Here is the mechanism. Wood chip mulch in contact with living soil is colonized by fungal networks, specifically by saprophytic fungi that decompose woody carbon. These fungi extend thread-like structures called hyphae into the soil below. Hyphae are between 2 and 10 microns in diameter. They penetrate pore spaces that plant roots cannot access. They redistribute moisture laterally, carrying water from zones of high saturation to zones of low saturation, functioning as a secondary irrigation network that operates 24 hours a day without human involvement. This is not a fringe theory. A 2017 study published in the journal Soil Biology and Biochemistry measured fungal hyphal water transport in loam soils amended with woodchip mulch. Researchers found that active hyphal networks increased available soil moisture in the surrounding 8-inch radius by 31% compared to non-amended controls, with no additional water input. 31% more available moisture from biology alone. The fungi also produce a compound called glomalin, a glycoprotein that coats soil particles and increases their ability to form aggregates. Aggregated soil has higher porosity. Higher porosity means greater capillary capacity. Greater capillary capacity means your Allah's moisture bulb reaches farther, lasts longer, and loses less to gravity drainage. The biology is improving the plumbing, and it compounds over time. Year 1, the fungal network is establishing. Year 2, it is expanding. By year 3, a well-maintained biblical garden bed moves and holds water in ways that would require thousands of dollars of engineered irrigation infrastructure to replicate mechanically. The ancient farmers did not know the word glomalin, but they knew that soil fed with organic surface material became darker, richer, and more water-retentive with each passing season. They called it blessing. We call it soil organic matter accumulation. The mechanism is the same. Tier 3 fungal colonization begins within 14 to 21 days of mulch application in warm soil above 55 degrees Fahrenheit. Measurable moisture benefit detectable within 30 days. Full network establishment by end of season 1. Compounding benefit from season 2 onward. 3 tiers. 1 addresses delivery. 1 addresses loss. 1 addresses capacity. Remove any one of them and the system still works, but at reduced efficiency. Keep all 3 and you have what the Nabatean farmers had. A garden that largely waters itself, built from a pot, some wood chips, and the biology God put in the ground at the beginning. There is one watering habit that undermines everything in this system. It is the most common watering habit in the modern garden, and there is a good chance you are doing it right now. Frequent, shallow watering. The practice of applying small amounts of water to the soil surface every day or every other day in quantities that penetrate no deeper than 2 to 3 inches. It feels responsible. It feels attentive. It looks like care. It is not care. It is training your plants to be helpless. Here is what happens inside the soil when you water shallowly and frequently. Water enters the top 2 to 3 inches. The root system detects moisture at that depth. Root growth follows moisture. This is called hydrotropism, the directional growth of roots toward water sources. It is not a preference. It is a biological imperative. Roots go where water is. If water is always at 2 inches, roots concentrate at 2 inches. A root system concentrated at 2 inches is living inside the evaporation zone, the same zone that loses 0.2 inches of moisture per day to atmosphere and summer heat, the same zone that reaches 130 degrees Fahrenheit at soil surface on a 95-degree day, the same zone that dries to dust within 36 hours of your last watering. You have not grown a garden. You have grown a dependent, a plant whose entire water supply sits in the most volatile, most exposed, most unreliable layer of your entire soil profile. A plant that begins wilting within 24 hours of a missed watering. A plant that cannot survive a vacation, a power outage, or a broken irrigation timer. This is not resilience. This is manufactured fragility. The research on this is not ambiguous. A 1998 study conducted by Kansas State University Extension measured root depth distribution in tomato plants under 3 irrigation regimes: daily shallow surface watering at 0.25 inches per application, every 3-day deep surface watering at 0.75 inches per application, and subsurface a la irrigation refilled weekly. Results at 60 days. Daily shallow watering produced an average maximum root depth of 4.3 inches. 87% of root mass was concentrated in the top 3 inches of soil. Every 3-day deep watering produced an average maximum root depth of 7.1 inches. 64% of root mass in the top 3 inches. Weekly alla irrigation produced an average maximum root depth of 13.8 inches. Only 29% of root mass in the top 3 inches. Same plant, same soil, same sunlight. The only variable was where the water was delivered. The alla irrigated plants were not just more drought tolerant. They were accessing a completely different soil layer, one rich in subsoil minerals that surface-watered plants never reached. The Kansas State researchers noted that alla irrigated tomatoes showed measurably higher calcium and magnesium content in leaf tissue analysis. Not because more fertilizer was applied, but because deeper roots accessed minerals that surface roots never contacted. Deeper water, deeper roots, deeper nutrition. The plant becomes what the water teaches it to be. There is a verse that speaks directly to this. Jeremiah 17:8. He is like a tree planted by water, that sends out its roots by the stream, and does not fear when heat comes, for its leaves remain green, and is not anxious in the year of drought, for it does not cease to bear fruit. Notice what Jeremiah does not say. He does not say the tree is watered from above. He does not say the tree is sprinkled. He says the tree sends out its roots toward the water source. The root moves to the water. The water does not move to the root. That is not a passive image. That is an active, directional, biological process. Hydrotropism, described with agricultural precision 2,600 years before the term existed. And notice the result. Does not fear when heat comes, leaves remain green, does not cease to bear fruit in drought. This is not a spiritually resilient tree. This is a physically resilient tree, one whose root architecture was built deep enough to access moisture that surface evaporation cannot reach. The fear, the anxiety, the cessation of fruit. Those are not emotional states. They are the physiological symptoms of a shallow-rooted plant in a drought. Jeremiah was describing 2 root systems, one built by shallow surface water, one built by deep consistent moisture. One fails in heat, one does not. The difference is not the plant, the difference is where you put the water. Modern drip irrigation, the system sold as efficient, as progressive, as the responsible choice, delivers water at the soil surface or just below it. Standard drip emitters wet the top 4 to 6 inches. Premium subsurface drip lines are installed at 6 to 12 inches and cost between $800 and $2,400 per $1,000 square feet installed. They approximate what an alla does for $3. The modern habit is not just inefficient, it is expensive inefficiency, and it produces exactly the shallow, fragile, drought-dependent root architecture that Jeremiah's tree was designed to avoid. You can break the habit today, stop watering the surface, put the water where the roots need to go, and let the roots follow it down. Let's put numbers on the table, not estimates, not approximations. Real figures from real systems. A standard residential drip irrigation system for a 4x8 raised bed, the kind sold at big box hardware stores as a complete kit, costs between $45 and $85 for materials alone. That includes the mainline tubing, emitter heads, pressure regulator, filter, timer, and fittings. Installation time, 2 to 4 hours for a first-time installer. Lifespan, 3 to 5 years before UV degradation of tubing requires replacement. Emitter heads clog with mineral deposits within 18 to 24 months in hard water regions, which includes most of the American Southwest, Midwest, and Mountain West. A clogged emitter delivers 0 water to the plant it serves. It fails silently. You often do not know until the plant is already stressed. Annual maintenance cost, $12 to $30 for replacement emitters, tubing patches, and filter cleaning. Water efficiency, 60 to 70% of applied water reaches the root zone under ideal conditions. In summer heat, that drops to 50 to 55%. Electricity required, yes, for the timer. Battery replacement every 12 months adds $6 to $12 per timer. Total 5-year cost for one 4x8 bed. Initial system, $65 average. Annual maintenance over 5 years, $100. Replacement at year 5, $65. Battery costs over 5 years, $40. Total, approximately $270 over 5 years. And at year 5, you start over. The plastic degrades. The timer corrodes. The tubing cracks. You buy it again. 3 OLAs for a 4x8 bed. Each OLA, $2.50 average for a 6-inch unglazed terracotta pot plus saucer. Plumber's putty to seal drainage holes. $3 for a tub that seals 40 pots. Approximately $0.08 per OLA. Total materials cost $7.74. Installation time 36 minutes. Wood chip mulch for the same bed surface. 4 inches deep across 32 square feet. Free in most regions from municipal tree services or arborist drop-offs. Lifespan of terracotta, indefinite under normal use. Archaeologists recover intact olas from 4,000-year-old sites. A pot buried in garden soil and handled with basic care does not degrade. It does not UV crack. It does not clog. It has no moving parts. It has no battery. It has no timer. It has no failure mode. Annual maintenance cost, $0. Refill with water every 3 to 7 days. That is not maintenance, that is use. Water efficiency, greater than 90% of applied water reaches the root zone. 0 surface evaporation from the delivery mechanism. 0 runoff. Electricity required, none. Total 5-year cost for one 4x8 bed, $7.74. The modern system costs 35 times more over 5 years. 35 times. For a system that is less efficient, less durable, and more likely to fail silently while your plants suffer. Now scale that up. The average American home vegetable garden is approximately 600 square feet. That requires roughly 50 OLAs fully installed, at a total material cost of under $130. One time, no replacement, no maintenance, no electricity. A professionally installed subsurface drip system for 600 square feet costs between $1,800 and $4,500 depending on region and installer. It will need partial replacement within 5 years, full replacement within 10. Over a 10-year period, the professional drip system costs between $3,600 and $9,000. The OLA system costs $130, and it performs better, not marginally better, measurably, consistently, permanently better, because its efficiency increases over time as soil biology develops under the mulch layer, while the drip system's efficiency decreases over time as components degrade. One system ages into weakness, the other ages into strength. There is one more number worth stating. Water. A 600 square foot garden irrigated by conventional overhead sprinkler uses approximately 1,500 gallons per week during peak summer in a hot climate. The same garden irrigated by olives uses approximately 450 gallons per week. That is a reduction of 1,050 gallons per week. Over a 20-week growing season, that is 21,000 gallons saved per year, per garden. At an average municipal water rate of $0.05 per gallon, that is $105 saved annually on water alone. In drought-restricted municipalities where tiered pricing applies, the savings can reach $300 to $400 per season. The system pays for itself in the first summer, and then it keeps paying every season, without replacement, without maintenance, without electricity, for as long as you choose to garden. Psalm 1:1-3 describes the righteous man as a tree. He is like a tree planted by streams of water that yields its fruit in its season, and its leaf does not wither. Not a tree that is watered, a tree that is planted by water. The positioning is intentional. The tree does not receive water passively from above. It is placed in deliberate proximity to a consistent, deep, reliable source. Its roots find that source. They grow toward it. They anchor into it. And because of that architecture, built slowly, built deep, built correctly, the leaf does not wither, not in summer, not in drought, not in the year when the rains do not come. The withering is not prevented by more water applied more often. It is prevented by root depth. What we have covered today is not complicated. It is old. There is a difference. Complicated things require expertise to maintain. They require replacement parts, technical knowledge, and continued financial input. They degrade. They fail. They need you. Old things, things that have survived 4 millennia of use across multiple continents and civilizations, are simple by necessity. Complexity does not survive 4,000 years. Only what works survives. The Allah works. The mulch works. The biology works. Not because someone recently discovered them, because they were never wrong to begin with. Here is what I want you to do this week. Pick one garden bed. One. 4 feet by 8 feet if you have it, smaller if you don't. Do the jar test. Do the compaction test. Write down what you find. Go to your local hardware store or garden center. Buy 3 unglazed terracotta pots, 6-inch diameter. Buy 1 small tub of plumber's putty. Spend $11. Install the 3 olas at 6-inch depth. Apply 3 to 4 inches of wood chip mulch across the surface. Fill the olas. Place the saucer lids on top. Then step back. Do not water the surface. Do not adjust anything. Do not intervene. Come back in 7 days and look at your plants. Then come back in 30 days and look at your roots. What you find in that soil at 30 days will tell you more about water, roots, and design than anything I can say in a video. The soil will show you. It always does. If this video gave you something useful, a number, a mechanism, a test you can run today, consider subscribing. New videos release every week. Each one follows the same approach. Scripture, science, soil, no products to sell, no ideology to push, just the oldest agricultural knowledge on earth, examined carefully and applied practically. If you have already installed alles in your garden, leave a comment below and tell me your soil type. Clay, sand, loam, amended, native, whatever you are working with. I read every comment, and if you know someone who is spending $300 a season watering their garden from above, share this video with them, not to convince them of anything, just to give them the number, $3, and $4,000 years of evidence that it works. The ancient paths are not primitive, they are proven.